is then converting from Cartesian coordinate into polar coordinate. All right, so to do that, some of the things that we need to recall are super quick. X squared plus y squared is r squared. So then this becomes r squared. And then we recall that x is equal to r cosine theta and y is equal to r sine theta. So by that, then we can take this and substitute it into there, giving me this. So when I get to here, then to actually solve, I'm going to move everything to one side. R squared minus 6r sine theta equals 0. I'm going to factor out an r. R equals, 1 minus 6 sine theta equals 0. All right, and my two solutions to that would be when r is 0, and that's not really an equation, or when this is 0. So my equation then would be 1 minus 6 sine theta. Sorry, that's not a 1, that's an r. There we go. So when r minus 6 sine theta is equal to 0, so my equation then would be r equals 6 sine theta. All right, check. So this equation in a Cartesian coordinate system is this equation, one more down, in polar coordinate system. And if you're wondering what that looks like, let's see, at 0, I'm at 0. At sine of pi halves, I am at 1, so that's at 6. So 1, 2, 3, 4, 5, 6. And I'm not going to be able to sketch it real well, but it ends up being a circle. Pretend that's a circle, if you will. So it ends up being a circle in polar coordinate system. And then converting from polar back into Cartesian, it's remembering these things as well. R cosine theta is x, r sine theta is y. So if I take this top one here and solve for cosine theta is x over r. Sine theta is y over r, so then I can plug that into my equation. Actually, first thing first, I'm going to get rid of my fractions. I'm not a big fan of fractions, if I can at all get rid of it. So I'm going to multiply everything by the denominator. 1 plus 2 cosine of theta. So on the left, I will have r plus 2r cosine of theta equals 3. Cosine of theta is x over r, so I have r plus 2r times x over r equals 3. Well, then the nice thing here is my r's reduce. I have r plus 2x equals 3. Does that help me? And then, oh yes, I'm going to solve for r. R equals 3 minus 2x. The reason why I want to do that is if I can get r by itself, I can then square both sides. The reason why, if I can square both sides, is I remember that this also is a true function when we're converting, just like cosine of theta, or up here, r cosine theta is x and r sine theta is y. X squared plus y squared is r squared. Over here, then I can replace that with x squared plus y squared. And then on the right, I can just leave that for now and be done. And there is now my Cartesian coordinate system equation converted from polar. All right, now, in the future, not too far off, we're going to go ahead and we're going to square this whole thing out and then move all of my things over, and then I'm going to complete the square, and I'm going to find what the actual center is of that circle as we go along. All right. So now what we're moving into in this next section is complex numbers. So complex numbers are in the form of a plus bi. All right, complex number field. If I were to graph things on the complex number graph, these are x's and these are i's. That's a backwards I, that's a j. This is an I. I just changed my color. This is an I. There we go. So if I wanted to graph that first one, just 4 plus 2i, if I were to graph it, that'd be over 4 on the x and then up 2 on the I, and that point right there would be 4 plus 2i. And that's how the complex coordinate system, right? So we've had the Cartesian coordinate system. I really quickly ran us through the polar coordinate system, and now we're talking about the complex number system, and then we're actually going to convert from complex into polar as well. All right, but that's what that point means. But up here, arithmetic, it's actually quite simple in terms of doing it like we do, thinking of I as a variable, even though it's not a variable. But 4 and then minus 5, negative 1, 2i minus a negative 5i. So minus a negative is plus a positive, so that's going to be plus 7i. Pretty simple, pretty straightforward. Distributive property works the same way, 8 minus 4i. But then when we get to multiplying binomials, you're going to have to FOIL this out because fun stuff happens when we do that. So when I FOIL it, I go first to outsides 8i, insides negative 3i, lasts negative 12i squared. Remember, the square root of negative 1 is I. So when I have I squared down here, I squared is the square root of negative 1 times the square root of negative 1, which is negative 1. So this ends up becoming 2 plus 5i minus a negative 12, which is plus a positive, so I have 14 plus 5i. And then we're going to get to things that look like this. They don't look a lot of fun, and they're not much like when we have rational expressions. If I need to rationalize the denominator, where we've seen things like this in the past. If you had 3 over the square root of 2, we'd say rationalize the denominator. And you'd say, oh, okay, I got to get rid of the square root in the denominator, so you multiplied everything by root 2 over root 2, and you would have then 3 root 2 over 2. Same idea, slightly different process. Because what we have to do is we have to figure out how do we get rid of the I. We get rid of I by using what's called the complex conjugate. Complex, because complex numbers, a plus bi. Conjugate would be this. We're multiplying it by 1. We're still multiplying it by the same thing in the top and same thing in the denominator. But it looks like the difference of squares. Remember when you used to do that? You'd have, if our equation or our quadratic was x squared minus 9, it factored into x plus 3x minus 3. If my quadratic used to be x squared minus 16, it'd be x plus 4, x minus 4. I was eliminating the middle term. Now what we want to do is, you're thinking about that when we're multiplying, I want to multiply it by something that eliminates that middle term, because the middle term for us now has the I in it. So to get rid of that middle term, this is what's called its complex conjugate. Because when I do that in the denominator, I will have down here 16 plus 4i minus 4i minus I squared, which will be 16 minus I squared. And I squared we know is negative 1, so it's 16 minus negative 1, which is 17 for my denominator when I'm done. In the numerator, I'm going to multiply, and again, FOIL that out. 8 plus 2i plus 20i plus 5i squared. That middle term will be 22i. That's these two. I squared is -1, so this becomes 5 times -1, which is -5. And then 8 minus 5 is 3. So it's my equal sign is kind of in a weird place. And so is my fraction bar. But when I simplify that, it simplifies to 3 plus 22i over 17. And the goal only was to eliminate the I in the denominator. So we rationalized the denominator in the complex number system. And now I could actually graph this as 3 over 17 plus 22i over 17, where I'd go 3 over 17 in the x direction. I'd go up 22/17 I, and I could plot that point. When it looks like this, I can't plot that point. So then now we're going to be converting from polar into complex. And you thought to yourself, why? Good question. It is applicable for some of you in the future, which is why we're doing it, and the rest of you are along for the ride. And besides, I think it's fun. So we have z is a plus bi, and z can also be written as x plus yi when we're converting. So a plus bi is just, that's the form we've been using for any complex number, some number plus bi, and we usually call that z. All right, so this is what it is in Cartesian coordinate system. We can also refer to it like this in Cartesian coordinate system. But then we see x and we go, oh wait, I know x in polar. X in polar is r cosine theta, and y is r sine theta. So z in polar is r cosine theta plus I r sine theta. Up here we did yi. I try not to put the I at the end, and you shouldn't either, because then it looks like the I might be inside of the sign, like sine of theta I. All right? Unless I'm going to put my parentheses and do that consistently, it's better to have that I out in front. IR, RI, doesn't really matter. So, all right. So now we've taken some complex number and I converted it into polar. What does that look like in an actual problem? Good question, you ask. So I'm going to start by taking 4i, the complex number 4i, and I'm going to convert it into polar form. So what I first need to think about is in my graph of z equals 4i, here's my graph, where is that point? Well, the point technically is, all right, because z equals a plus bi, the a is 0, so my x-coordinate is 0. So it's 0 plus 4i, which means I'm 0 in the x direction, 4i, so that point right there, that point is 4i. And then, in order to put it into polar, I'm going to look and say, all right, well, what is the theta of that location? That theta is pi halves, as I think about a polar coordinate system up here, pi halves. Move that up. So then, instead of r cosine theta, I'm going to have z equals, what's my radius? How far away am I from the origin? I am 1, 2, 3, 4 up. So I am 4 cosine of pi halves plus 4i sine of pi halves. Now, if I would actually find cosine of pi halves and sine of pi halves, right? Sine of pi halves is 1, cosine of pi halves is 0. It would simplify into z equals 4i. Because the cosine of pi halves is 0. 4 times 0 is 0. The sine of pi halves in my unit circle is 1. 4i times 1 is 4. But I'm going to leave, in terms of converting it into polar, I'm going to leave it here, and then I'm not going to keep simplifying. And the reason why is eventually we're going to be talking about graphing and then variables and all sorts of things from there. So this is what's referred to as Euler's method. Euler's method is that z equals r cosine theta plus I r sine theta is actually the exact same thing as r e. E is Euler's constant, 2.71, yada, 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 yada. All right, r e to the I theta. So if z is negative 8, which is actually negative 8 plus 0i, I can do that into Euler's formula pretty quickly. Z equals, and if you think about, again, when you're thinking about the negative 8, you're thinking about where is its location. X, I. Out here at negative 8, that's the dot. Because there's no I, so it's just at negative 8. So my radius is 8. E to the I, and what is my theta? To there. My theta is pi. Once again, when you're given something in complex form, think about where it's plotted on the complex graph. Then think about the corresponding theta that gets you there when we go to polar. And then my distance from the origin. 8 is my distance, and I'm at pi. So it's e to the I pi times 8. This will be the more preferred way. This is not wrong. It's just clunkier. What if it's not just a simple one number, so I don't know the radius right away? Again, we start with the negative 4 plus 4i, graph it, plot the point. I need to find r. This is where you recall, oh yes, Pythagorean theorem. All I have there going on is this right triangle. It's over 4 and it's up 4. So r squared is equal to 16 plus 16. R squared equals the square root of 32. R equals 4 root 2, plus or minus. So that's my r for my radius. Euler's is z equals r e to the I theta. Z equals, is it plus or minus? The answer is it's plus, because radius is only going to be a positive distance. So it's 4 root 2 times e to the, now my little label there actually looks like it's in the right spot for what I need. But it's e to the I, and then what's my theta value? How far did I go, again, from that starting point of 0 degrees over to 4 plus 4? One of two ways about going and doing it. One, you could recognize that, well, 4 over, 4 up, that's a 45-degree angle. So pi fourths, pi halves, 3 pi fourths. Or you look at that and say, okay, theta is going to be, so if I were to do sine of theta is the x-coordinate over the y-coordinate. No, y-coordinate over the hypotenuse. And the y-coordinate would be positive 4. The hypotenuse is 4 root 2, which is equal to 1 over the square root of 2, which is equal to root 2 over 2. But then that doesn't tell me which what quadrant I'm in. I'm in the second quadrant, so my sine is also positive in the second quadrant. That's how I get to 3 pi over 4. If I did cosine over theta, it'd be negative 4 adjacent over hypotenuse, so negative 4 over 4 root 2. Be a negative root 2 over 2, so then you can know that cosine, we're in the third quadrant there as well for 3 pi over 4. Or, again, identifying that this is 4 over and 4 up. That's the quicker way. It's one of some numbers that aren't quite as convenient that you got to do a little bit more work to find out what my theta is 4 degrees. I don't even know how to pronounce his name. De Morvier, he's French. So if you know French, pronounce that out for me, but that's as close as I'm going to get. So his theorem is this. if z is this, then for any integer n, integer, remember, is a positive or negative whole number value, z to the n is r to the n cosine of n theta plus I r to the n sine of n theta. How does that help me? Good question to ask. If I have something like this, and I don't want to multiply it all the way out to 6 powers and then work my way back through to find it, I can do it faster by first saying, okay, where is this located? It's square root of 3 over and it's I up. R squared is x squared plus y squared. So r squared is 3. Square root of 3 squared is 3. My y, the number in front of the I is 1, so y squared is 1. 3 plus 1 is 4, so r is 2. So the radius right there is 2. And then I have z equals, so I don't have z to the 6th. I'm not going to do the 6th yet. I'm just going to look at just this one. If I can just find this one first, so that will be 2e, because it's re, to the I theta. Theta, that angle that's in between here. All right, theta is opposite over hypotenuse, which is the 1 over 2, which is the radius. Cosine of theta is the square root of 3. That was the adjacent side. That was this length. Square root of 3 over 2. What angle has a sine of a half, has a cosine of square root of 3 over 2? The answer is theta equals pi 6. 30 degrees. It will be I times pi 6. But now I have it to the 6th power. Using de Moivre's theorem, I will have z to the 6th equals 2 to the 6th. Cosine of 2 pi 6ths plus 2 to the 6th I sine of 2, that's times pi 6. So I have here square root of 3 plus I to the 6th in polar is, and I'm going to factor the 64 way out in front, and have cosine of pi thirds times I sine of pi thirds. Because if memory serves me correctly, 2, 4, 8, 16, 32, 64. Yes, 2 to the 6th is 64.